So in this video, I just want to do a bunch of examples of double integrals. Okay, just over rectangular regions for this one. So let's find the integral over r of xy minus 3xy squared dA, where r is equal to x and y such that 0 is less than or equal to x, less than or equal to 2, 1 is less than or equal to y, is less than or equal to 2. I think I'll just write the interval cross interval notation in the future just to save some writing time there. Okay, so this is going to be equal to, it doesn't matter which one we do first, so let's just do x or y first this time, which might make it harder. Generally, one of the regions will be easier, not necessarily when we have numerical bounds like this, but when we get into the trickier regions, some of our bounds will be the other function, and then it'll actually really matter which one we do first. Here, it shouldn't really make too much of a difference. So we're going to integrate with respect to y first. Okay, so y squared over 2. X is treated as a constant here, remember. And that's going to be xy cubed. And then this is going to be from y equals 1 to y equals 2. And then we're doing dx. Okay, and then, oops. This is going to be, plug 2 in and you get 4 divided by 2 is 2. So 2x minus 8x, looks like. And then minus x over 2 plus x. Okay, dx. So we can simplify that quite a bit. That's going to be 3 minus 5x, and then minus a half x. So we're at 5.5, so like 11x over 2. Okay. Okay, and then when we integrate that, it's going to be 11 over 4x squared from 0 to 2. Okay. And then that's going to be 11, and that's it. Okay. It looks like I forgot a minus sign somewhere, right? This was supposed to be negative. Yeah. Okay. So we get negative 11 for that one. So, if you want more practice, you could try doing it the other way. Do it with x first, and then, make sure you get the same answer. It's basically going to take like a really weird function to not get the same answer. Like I said, the real criteria you need is that the function is not measurable. And when you get into all that, like with measurable functions, it takes a lot to make functions that aren't measurable. They're not just going to happen by accident. Basically, any function you could reasonably think to write down should be measurable. So it shouldn't be an issue anywhere. Let's do a trig example. I like to just remind ourselves of trig every once in a while. It doesn't pop up a lot, but it does sometimes, so it's good to be aware of it. Okay, over 0 to pi over 2 cross 0 to 1. Okay. So again, doesn't matter which one you do first. I guess we could just do the x first this time, just because. Okay, so the integral of cosine, if you remember, is sine. So this is going to be, well, e to the y is just a constant, so it's going to be e to the y sine of x from x equals 0 to x equals pi over 2 dx. Okay, So we have e to the y, and then sine of pi over 2 is just 1. And I guess we're just going to have e to the y, right? Sine of pi over 2 is 1, and then you're going to have minus e to the y sine of 0, which is 0. So it's just going to be e to the y, actually. So I guess this is just going to be e. E minus e to the 0, right? Because you plug in the bound, so it'll be e minus 1. Okay. Okay, let's do this one here, where f of xy is equal to 4xy over 0, 1 cross 0, 1. Okay. And we'll do this one a little bit differently, because notice that this is 4x times y. We could have done the last one like this too. So we can think of it as two different, a product of two different functions. So let's just see how that works. So f of xy dA will be the integral of 0 to 1 4x dx times the integral of 0 to 1 y dy. Okay. Now I really never really do them like this, except for in the tricky cases where you have to, like e to the negative x squared, because I don't really think it makes it any easier necessarily. But we can just see the example here. So this is going to be 2x squared from 0 to 1 times y squared over 2 from 0 to 1. Okay. So that's going to be 2 times 1/2, and that's going to be 1. Okay. This is actually from a problem showing that this is a probability distribution function. So again, those have to integrate to 1. So here we just showed that it does. Okay. This one is a little bit different, but same kind of idea. We just have to kind of find the bounds on our own a little bit here. So find the volume of the solid S bounded by the elliptic paraboloid 2x squared plus y squared plus z equals 27. The planes x equals 3 and y equals 3. And the 3 coordinate planes. Okay. So first of all, notice that the function is not explicitly in terms of z, but it very easily can be solved for z. And then notice that it doesn't actually explicitly give us the bounds, right? It just tells us that it's bounded by the planes x equals 3 and y equals 3 in the coordinate planes. So the coordinate planes would be, where they're all 0. So this is basically trying to tell us that it's bounded, x is bounded between 0 and 3, and y is bounded between 0 and 3. Okay. So there's really not much more to do. We just need to solve for z first of all. So 27 minus 2x squared minus y squared. Okay. So the integral here is just from 0 to 3 of both of these. And it doesn't matter which one we do first. Okay, so let's do x first, I guess. So we got 0 to 3 of 27x minus 2x cubed over 3 minus y squared x I think it's easy to forget to put that this is a constant, so we got to put an x on the end of it. X equals 0 to x equals 3 of dy. Okay. So that's going to be 27 times 3, what's that, 81, minus 8 times, or no, 27 over 3 would be 9, and then times 2, we got 18, and then minus 3y squared, and then the zeros will all just be 0. Okay. And then we'll go ahead and integrate that. So we got 81y minus, I guess I could combine those. What's that? 62 or 63 rather. Right. So 63y minus y cubed from 0 to 3. So we'll get 63 times 3, which is 189 minus 27. So we'll get 162. Okay. So ultimately, there's really not much more to these integrals than there is in the single variable case. The problems are really, they're just going to be as difficult as the integrals are, right? All the integration techniques will still work. Like you can still use integration by parts, or, you know, integration by substitution or whatever. Just keeping in mind that the opposite variable is a constant. And those are the kind of cases where you might get to a point where doing one variable is easier first if it's much easier to integrate that variable. But again, that'll be more relevant when we look at different bounds where the bounds are one of the other functions. Okay, but ultimately, mechanically, you know, we're basically just doing two integral problems in one.